Earth is immense, but we only live on a thin shell of its surface. So what if we built a planet with only that thin shell, or with several layers of them? So today we'll be discussing why and how you would build hollow planets, what we often call shell worlds, as well as multi-layer concentric designs, the Matryoshka shell world, and we'll also touch on hollow moons and hollow suns. I want to emphasize that much like when we discussed building flat Earth megastructures, these are serious designs with a lot of logic behind them, for man-made planets humanity might one day build, or which other civilizations that might exist elsewhere in the universe might have built. We are not really interested in conspiracy theories claiming our own planet might be a hollow Earth, but as we'll see today, you could build a hollow planet that would convincingly fool even modern science into thinking it wasn't hollow when it actually was. So we can't exactly say hollow Earth is debunked, especially since, as we'll also see today, there is very good motivation to construct hollow planets and shells as opposed to classically terraforming Earth-like planets. We probably should start by noting that there is no single unified hollow Earth theory, as it describes a lot of theories ranging from the scientifically coherent to pseudoscientific to simply fun plot devices for fictional stories. Those last are equally important to us because when you are in the mega engineering game, you build to what people want as much as to what is practical. So if people want a firmament that is shot through with massive caverns and underground ecosystems, like the Underdark common in various D&D settings like the Forgotten Realms, then you build them a firmament that looks like a Swiss cheese with extra large holes. And this is one common approach to Hollow Earth, merely that the upper layer has a lot more underworld space than our own planet. Indeed, this is a scenario many planets might have, not just from naturally occurring lava tubes, but as a byproduct of a civilization mining its surface for many millennia, or even some larger species that acts like ants and burrows immense caverns akin to scaled-up ant hives. One of our recurring points today will be that hollow space saves mass. This is especially true in regard to the mass of valuable elements used for construction like carbon, aluminum, or iron, as opposed to hydrogen or helium. Thus, a lot of artificial planets, be they shell worlds or rotating habitats, probably do go heavy on hollow underworld layers with lots of caverns filled with mushroom forests and underground lakes, because it saves valuable mass while adding an interesting feature for residents or visitors. Of course, in most versions, it is not simply far more caverns with lost world civilizations inside them. It's entire extra layers of planet, sometimes even with their own lighting. Imagine, if you will, a world beneath our feet that is not composed of molten lava and a fiery core, but of vast unexplored caverns, mysterious landscapes, and possibly even civilizations thriving under the radar, quite literally. The main Hollow Earth theory has its roots in the imaginations and speculations of thinkers and writers through the ages, from Edmund Halley himself, for whom the comet is named, proposing in the late 17th century that Earth might consist of several concentric shells, to John Cleves Symmes Jr. in the early 19th century, who famously declared the Earth to be hollow and habitable within, inviting explorers to find these entrances at the poles. Symmes' call to adventure, however, seemed to overlook the slight inconvenience of freezing temperatures and the absence of any giant openings below. We in modern times can now laugh off the notion of vast underground chambers or lakes beneath the poles, except of course for the many vast chambers and underground lakes we found under the Antarctic ice, like Lake Vostok, the largest of Antarctica's several hundred known subglacial lakes, which is the 16th largest lake on Earth by area and the 6th largest by volume. There is life in there too, though thus far we've only found bacteria and fungi, and it isn't hard to imagine a more energy-abundant civilization might float little fake suns around in underground lakes and seed them with some photosynthetic life. just a big floating fusion reactor with artificial lighting as its outer shell, or that an underground lake like this might have thermal vents bringing in nutrient and energy from deep underground, or that a civilization might make some or add more vents. Now, Hollow Earth itself can be a bit of a misnomer. Unlike the shell-walled megastructure we'll discuss in a bit, it usually is not assuming the planet is a thin shell or crust around emptiness. The exception to that are versions in which people live upside down on the inner edge of the shell, and all the heat from below that we get is not a hot molten core, but rather a sun of some sort shining up on these folks living upside down. This has the same problem a classic Dyson sphere has. There's no gravity there. The nature of gravity is such that if you live on the surface of a sphere, you feel downward gravity toward the center, and if we hollowed it out, those on the surface still feel gravity in that same direction, albeit weaker from the removed mass. But if you are inside a spherical shell of mass, then you are not only weightless at its center, as folks tend to expect, but weightless anywhere inside it. Even standing or grabbing onto the inner side of a shell, touching one side of it, still results in all the other matter pulling on you evenly for net zero gravity. A neat side effect of this is that if we wanted to add another layer to Earth, we could build one higher up, a huge massive spherical shell more people could live on, and it would have zero effect on gravity down here on Earth's original surface, but it would generate more gravity for those living on it, and would also add its gravity to another layer above it if we built one, helping keep gravity from weakening as you went further from Earth's center. Coming back to Hollow Earth theory and its more modern incarnation, in an era of better knowledge of astronomy and geology, it is a theory that has been kept alive by science fiction writers, conspiracy theorists, and the occasional adventurous spirit wearing a tinfoil hat as a fashion statement. The allure of hidden worlds is irresistible after all. Who wouldn't want to believe in a secret utopia beneath our feet, complete with its own sun, ancient and advanced civilizations, and exotic wildlife, possibly including things we believed extinct like dinosaurs? And of course, this is part of its appeal to us when we contemplate building hollow worlds. We could go through the mainstream science, patiently explaining the plethora of evidence supporting the fact that Earth is indeed mostly solid with a molten core, but I suspect very few of our viewers are in doubt on this. Maybe we should anyway, since I don't think most folks know why we believe in a molten core or how we've proved it, but the short version is that when we have earthquakes, the seismic waves travel through the planet, and the speed they move at is based on the material they are moving through. Detecting these from different angles and distances lets us map out the interior. It also basically ruled out a hollow interior unless the folks crafting it had gone to fairly extreme efforts to mimic the surface seismic effect of a quake originating deep in the mantle and spreading out over many hundreds of miles on the surface. Though building such an artifact is an extreme effort, so we shouldn't go assuming they wouldn't include such an add-on, and they could do it. It wouldn't be that hard to have your earthquake machines on the inner side of the shell set to vibrate while synced at the right timing, frequency, and strength to full seismologists. It rather depends on how badly you want to mimic a regular planet, and how much the cost savings and benefits are to using a hollow planet over one you found and terraformed or built with regular planetary matter. So while the Hollow Earth theory enthusiasts hold on to their belief with impressive tenacity in an era where Google Earth can show you every inch of this planet's surface, we can at least recognize that the idea of vast, unexplored territories just a mole man's journey away is an undeniably appealing idea. You might not want to pack your bags for an expedition to the center of the Earth just yet, as the journey through the planet's crust might be a tad warmer and more solid than expected, but the Hollow Earth theory remains a delightful detour into the world of what-ifs and why-nots. After all, in the grand tapestry of the human imagination, who's to say there isn't room for a little hollow space? And so we see their appeal and can now ask, might we build such a thing, and if so, why? Here's the key reason, and it's a big one. We believe most of the matter in this universe is composed of dark matter, a substance whose only two known and fairly definite traits are that it generates gravity like normal, and that it doesn't interact with much of anything, meaning it's useless for building out of, but if you could trap it in the core of a fake planet, it would give you tons of free gravity, without needing to use valuable construction materials. Indeed, you need do nothing to keep it there. It interacts so weakly that every particle, once in place inside that shell by some unknown means, and at a velocity less than the escape velocity from inside it, would simply have every particle of it remain in there on 100 trillion lonely and undisturbed orbits. It is literally the ideal material for building fake planets out of, hyper abundant and good for nothing else. Artificial black holes are next on that list of ideal gravity generators, barring some actual artificial gravity devices such as those ubiquitous in science fiction. But first, let's talk about an alternative to dark matter. After all, we barely understand the stuff. There are still many scientists who are pretty skeptical if it even exists, and we have no obvious pathway to manipulating it to gather it up into handy little planet-sized spheres. Something very prone to gathering into little planet-sized spheres is regular matter, and most of that is hydrogen and helium. Helium bonds to nothing, and thus can't be used as a construction material, and while hydrogen bonds to plenty of things usefully, it is so abundant that there's not enough of everything else for it to bond to. So we can store it up in big spheres to use it for gravity and possibly one day trickle it into fusion reactors or stars themselves to extend their lifetimes, while removing their heavy elements via starlifting to provide construction material. The problem is that by default, a ton of hydrogen and helium in one spot is a gas under pressure, or fluid anyway, and only when we cram in more of it than the mass of a planet like Earth do we get enough of it packed in dense enough to offer Earth-like gravity, rather than something weak like lunar gravity. We'll get to hollow moons in a bit, but for the moment, we want an Earth-like planet. Of course, we might want something bigger than Earth too, and a shell built around Saturn just over its atmosphere would have very nearly the same gravity as Earth, with very nearly 100 times the surface area. Some folks might be wondering why this shell isn't simply falling inward, and of course channel regulars are thinking of active support methods like orbital rings and Atlas pillars, but we will return to that in a bit too. We might start by asking why the crust of our own planet doesn't simply fall into the core, and in point of fact it actually does over long enough periods of time. The continental shells are basically rafts floating on magma and are not eternal or stationary. Simple buoyancy keeps these rafts afloat. The Earth is the densest known object in the solar system, and the core the densest part of it. The mantle has a lower density of about 3.4 grams per cubic centimeter, or 3.4 times that of water, while the crust is around 2.6. We often refer to this density as specific gravity, without other units, and water is one. Denser objects are higher, like the iron in our planetary core, which is 7.9. Even that's a little too simplified, as the core, mantle, and thin shell of the crust all have additional distinct regions or layers with different properties, and if we feel like engineering an artificial planet, we probably stop at one of these layers and then have to simulate the effects of the others to the degree needed or desired. But while rock, magma, and metal are a lot denser than water, compressed hydrogen and helium are not. Hydrogen at standard pressure and temperature, or STP, is 0.09, less than a tenth of water, and helium is about double hydrogen at 0.18, whereas Earth overall is 5.51, 30 times denser than helium and 60 times denser than hydrogen. So we can compress them, but now we need an airtight shell or balloon to keep them packed in, and if you puncture it, then material will go venting out. Now that's not that big a deal, especially if it's chemically inert helium, but hydrogen venting out into an oxygen-rich environment is one match away from igniting. But even here, it would be no worse than a volcano and probably gentler. The question is how thick your fake crust is to resist puncture, and anything over a kilometer isn't likely to puncture even against a nuclear strike or asteroid less than a kilometer wide. You also have means of sealing them, such as putting a patch on, and we could imagine big sturdy bubbles filled with a slightly lighter mix of gas floating inside the gas interior that would float up into a puncture and seal it too. or just drones living on the inner surface of your shell, walking around with magnetic boots perhaps, that would go over and seal a crack. Problem is, you don't want a thick crust here either, as you are essentially making a balloon, albeit one vastly stronger than any rubber balloon. Those expand as gas pressure inside rises and stretches the balloon, which resists by elasticity. Here, the resistance is raw gravity, as that surface shell is being pulled down. So long as you are keeping it reasonably airtight, some leakage is fine, the gas pushes up and out, and the shell pushes in and down. On Earth, or a place with surface gravity akin to Earth, roughly every 10 meters of water or 4 meters of crust is adding 1 atmosphere of pressure downward. So by the time you're even 1 kilometer down, you're up to something like 250 atmospheres of pressure holding your balloon together, and that gas is pushing back at whatever pressure its density and temperature has, which is lowest up near the shell and highest in the core. Unlike a normal pressurized vessel, it's not got the pressure evenly distributed throughout. It will also depend on the temperature you keep that gas at and the actual ratio of hydrogen to helium. At a certain point, these materials will also be crushed into liquid hydrogen or helium or metallic hydrogen, and of course on the far end of this, you can ignite fusion. There will be some ideal surface depth for a given planetary radius, gas mix, and internal temperature. The extreme version of this is the edosphere, which assumes a steel shell a third of a mile or 500 meters thick around a gas ball 37 times wider than Earth called an edosphere, and which does have much lower gravity than Earth. The smaller you want it, the thicker or denser that crust needs to be to keep it going. This general class of artificial planet is called a bubble world, and really is not suitable for building planets that aren't a lot larger than Earth. Generally something the size of Saturn is contemplated if your goal is to have Earth-like gravity. If you want a certain crust thickness and your density isn't optimal, you can go thicker by including lots of hollow pockets, or other type of hollow Earth with a vast amount of underground caverns. You could potentially emulate magma with something cooler. Lead has a higher density and lower melting point for instance, but I generally don't think of volcanic activity as something you want to import to artificial planets. And as we discussed in giving Mars a magnetosphere, there are so many better ways to protect a planet, including with an artificial magnetosphere, than by using quadrillions of tons of molten and radioactive metal. These shells are also a great way to make storage for hydrogen and helium you want to later use for fusion or refueling a star. And as an example, a bubble world of Saturn's mass, with 100 times the living area of Earth, could store 25 million years of fusion fuel for our Sun. You could stick 100 of these in an orbital circle around our Sun, out where Earth is, and this is called a Kepler-Rosette orbit and is reasonably stable, and in the process, get 10,000 Earths worth of living area, all while storing your fuel to keep that star running for another 2.5 billion years. And you can, via star lifting, keep your star going indefinitely by pulling out the helium from your star to fill such hollow worlds and inputting new hydrogen from your planetary tanks. See our episode Refueling the Sun for details. Speaking of suns, you can also decrease the wavelength of any star or stellar remnant by building a sphere around it of tungsten or some other alloy that melts at a temperature similar to our own sun's surface. You place it at a wider distance where the total radiation coming off that star, white dwarf, neutron star, or black hole would be absorbed and re-emitted at that lower temperature and peak wavelength. Hollow stars like this allow you to adjust the spectrum of hotter stars to the color or temperature we prefer, and avoid the huge amounts of ultraviolet or even X-rays and gamma they might give off. This method can also be used to handle stars that are less stable in their output, as a thicker shell will absorb energy over time but emit it as a more stable black body emission. This can also contain coronal mass ejections and solar flares. You can also use this technique with smaller or cooler stars by making the polar regions of the outer shell reflective and the equatorial band the planets orbit in clear, or again of tungsten if you need to bring the temperature down again, or normalize the spectrum and output. We call this star boosting, and it is a way to adjust cooler stars to produce a hotter spectrum and more strongly in the disk their planets orbit in, widening its habitable zone. Shells like this don't necessarily need to be very thick or have any active support. See our episode on statites and ligites for the mechanics, but they should be able to float by radiant pressure holding them against the gravity. Now on the smaller size, getting back to the shells held up by internal gas pressure pushing back against a more modest gravity. These are often called gravity balloons, and we contemplate them for asteroids, where we expand an asteroid into a thin, hollow shell and fill it with either a breathable gas mix or some thinner mix of hydrogen and helium. Here the purpose is just to keep the gas in and give it a protective shell of matter against micrometeors, accidents, or attacks. And your gravity is either very minimal or generated by rotating habitats floating around inside the gravity balloon. They might maintain position by using thin air sails or by simply being tethered in place. Such structures have a lot of options for internal use. One other variation of this is the hydro shell, where the balloon layer is covered in water to allow very deep oceans, but at much lower pressures than such depths usually would have. We discussed those in our episode on marine space habitats, and we noted there with enough water you don't even need a filling for the shell, especially as we don't want tons of gravity. But in that case you do need active support to keep the shell going. However, these are a nice pick for hydrogen and helium filled shells, since they are naturally lower density, benefits us in keeping lower gravity and lower pressure in those oceans above the shell. The hydrogen could then trickle feed large fusion reactors on the shell, powering long vertical lighting towers for the ocean and pumps to churn nutrient and air through the water. An example of what I like to call vertical reefs. This low gravity issue from a gas filling of the shell will generally be true of any other hollow Earth designs we discuss, though there are some specific options for using a dim red dwarf or even a white dwarf with a very careful balance to avoid a nova to keep your gas hot and at higher pressure, while providing an equivalent to geothermal heating. You might want a lot of geothermal heating too, as you might not be planning on lighting this artificial planet conventionally by orbiting it in the Goldilocks zone of the star. As we discussed in colonizing white dwarfs, you can build large, wide ring-shaped bands around a white dwarf or gas giant as an alternative to this balloon approach. And you can also build a large, actively supported spherical shell that holds itself up through orbital mechanics. We've discussed it in detail in other episodes like orbital rings or space towers. But the abridged form of that is that if I place a small, ferromagnetic sphere, say iron, in a circular orbit around a planet, and then a bunch more, to form a loose ring, maybe even chain them together to help keep their spacing on their ring, I can now wrap that ring with a thin sheath, something magnetic that will keep it from touching them or drifting into them. Now, if that sheath is rotating with them, all is well. But we can also make it stationary to the ground below, and they'll keep spinning within it like water through a hose. But we need to spin them a bit faster in this inner ring to make up for the missing orbital momentum the outer ring or sheath is missing by being stationary. There's no complexity to this scientifically, it really is that easy, but it will leak energy unless you're using superconductors, and you need to magnetically shield it for safety, which can be tricky. But this is an orbital ring, and you can scale this up and put many next to each other to make a band you could build a big stationary hab on, or layer them up like thread on a soccer ball under the surface patches to build a rigid sphere you can live on. The cousin to this is the Atlas pillar, which simply runs this sort of matter chain up a long vertical pillar and back down again, and holds a platform on top by the same mechanics a piece of paper would use to float atop a heat vent, or if we blasted the underside of something with a water hose to hold it up. By encasing such a device inside a closed loop, which might need some power added to handle slow heat loss, you have a structural pillar that can hold weight up better than any known substance. We deep dive these more in other megastructure episodes, so we'll leave it there for the moment. And their value to us is that they let us make a hollow sphere at whatever distance from a chunk of mass we like. Once planets get bigger than Saturn in mass, they don't really get much bigger. Jupiter is only about 10% wider than Saturn. Indeed, as we add mass, they will stay about Jupiter-sized all the way up through brown dwarf levels up to red dwarf size at about 25,000 times the mass. The gravity on the surface of a shell right around this would be murderously high, 250 times that on Earth, so if we want Earth gravity, we would need it to be wider, indeed wide enough to have 25,000 times Earth's own surface area, or the square root of that, about 150 times wider than Earth. Needless to say, that leaves us a huge empty vacuum around that brown dwarf. You can't rotate a planet that big on a 24-hour day without having vastly lower gravity at the equator from the centrifugal force, meaning you either need to make it more egg-shaped, or live with the lower gravity there, or just put a fake sun around it that orbits your mega-Earth geocentrically, or possibly a Kepler rosette of several of them. We played with variations of that more in our episode Mega-Earths. This is how shell worlds work. Your gravity goes down inverse square to force, so to maintain the same surface gravity, you need to increase your mass with the square of your sphere's radius, which is also what your surface area rises with. Thus, any Earth-equal body, when it comes to gravity, has the same mass-to-surface area ratio Earth has, 100 times the mass, 100 times the living room, 100th the mass, 100th the living room, or living area. Living room can be increased on any of these by adding in hollow pockets throughout your shell, like those versions of the Underdark or Hollow Earth, and you could light them. You can also add concentric shells, and these don't need much more mass, just enough to compensate for the extra radius. If your next shell is 1% further out, then gravity will have dropped to 98% of normal, and you need that shell to have about 2% of the mass of the body below it to keep the gravity the same. You can keep adding layers indefinitely, but if you're lighting them you will have heat dissipation issues. We discussed options for that in Matryoshka's shell worlds, including potentially transforming Earth into such a world, or even scaling us up slowly through more and more layers into a birch planet, an enormous construct with a mass closer to that of a galaxy than a star, let alone a planet. You also need power for these things, which is where building them around a dim red dwarf or a cooler white dwarf often comes into consideration. But those are huge, and as we've noted elsewhere, we can also build them around even bigger neutron stars or black holes, which are vastly better power sources. The neat thing about black holes, though, is that while they only form naturally from stellar remnants about 1,000,000 times more massive than Earth, we believe we can make them artificially a lot smaller than that, and under current theory they could exist even at masses much less than Earth. This allows hollow Earths much smaller than our planet, such as asteroids or moon-sized ones, as you can fill that black hole up on cheap hydrogen, helium, or dark matter to the desired mass and then trickle in more to keep the active support powered and provide any power needs you have. Black holes make awesome fake suns too, especially if you cram one into something the size of a small moon made of a tungsten shell and fill it with gas of the right density that the black hole will absorb just enough to release energy to keep that gas hot and high pressured, and heat that tungsten sphere to just under melting temperatures to make a nice fake sun that you can orbit your giant fake planet with. There's also no pressure and drag issues inside these planet shells, unless you're making an artificial sun from it, with a black hole in the middle, so you can build lots of layers or even fill the interior with a swarm of rotating habitats orbiting the black hole, or more strip worlds or bracelet worlds that ring the black hole. These type of ring worlds need not be evenly distributed either. You can make them wider at certain places to be more like an orbital plate, which is basically where you hang an artificial continent over a planet that's held up by orbital rings that extend thinly beyond it or Atlas pillars. You could also make a ring just a bit smaller in radius than your shell that's spun inside it, offering centrifugal force as gravity but upside down, like we imagine for classic hollow Earths. Indeed, the mass of the outer shell permits the ring to exceed normal tensile strength limits on radius, as we discussed in our episode on Banks orbitals last month. By these technologies, you can take any planet, moon, or asteroid and give it Earth-like gravity, which is why I like them for options like terraforming the moon, and they are a key component of building a lot of the cooler constructs we discussed in the Megastructure Compendium, as an alternative to always using spin gravity on rotating habitat variations. Though as mentioned, we can use that to give us wide bands on the underside of each shell to also live on, and share the lighting of the next shell below it. Indeed, those bands can actually provide the active support for the shell above them. The downside of shell planets is they use way more mass per unit of living area, but a lot of it can be from low-value mass like hydrogen and helium that you are at best storing for future use in fusion or black holes. And with multiple concentric layers, or lots of vast hollow underground chambers, you can add living areas without needing more mass. Indeed, this same sort of active support technology allows you to safely shore up caverns miles wide without fear of collapse, especially without having to worry about earthquakes. And an Atlas pillar losing power just begins to slowly lose strength, so it's not like you flip a switch and the thing crashes down. One made from room temperature superconductors wrapped in a good magnetic shielding needs no power after being built, in theory. I'm sure practically speaking it would lose some anyway, but might lose energy so slowly that it took millennia to get a noticeable drop in strength. And redundancy is always a good idea. Build more than you need and have plans for if someone wants to blow them up. That's a good point to close on, as I think everyone can see how awesome these things are for all the options they give us, letting us make more planets and ones closer to Earth than naturally occurring ones we'd have to terraform. Indeed, they might be better than Earth in many ways, and that includes safety. Just like a building we make can be stronger than a natural shelter, a planet we build can be tougher and safer. People hearing about shell worlds sometimes flinch from the idea of living over a black hole or a small star, or over untold tons of hydrogen gas that might vent into their atmosphere through a crack and catch on fire. These are not honestly that big of concerns, but to contrast it, remember that the planet we live on is a thin crust of rock floating on a molten sea, whose dense and radioactive core is hotter than the surface of our sun. We regularly have volcanoes go off that have more force than a nuclear bomb, and some that have more energy than every nuclear bomb we ever made, and beset by earthquakes and asteroids too. A planet we engineer and build can be tailored to minimize these things, even weather issues like hurricanes, and just represent a better option, in my opinion anyway. Let me know what you think in the comments on the episode. And don't forget to hit like and subscribe while you're at it. And to close, keep in mind that while we probably don't live on a hollow Earth, it has a lot of attractive options going for it, so we may build them in the future, and indeed we may transform Earth into one someday, and truly live on, or in, a hollow Earth. As we saw today, it is not very likely our planet is hollow, whatever conspiracy theories might say. But another thing conspiracy theorists often worry about is getting spied on. And on this one, they're right. There are all sorts of folks gathering your data, some openly and honestly, others are bad actors and hackers, and many more are a bit shady at best. Whatever their motives or intentions, that's your data they're grabbing and selling and trading, right out there where anyone can Google you up, and now they're doing it with the help of AI. You do have the right to make folks take your data down, but it would take you years to do it manually, just once, and by then it would be back up again on some other site, harvested again by AI. That's where our sponsor Incogni comes in. They use AI too, in order to find your information online and send automated takedown requests on your behalf. All you have to do is sign up, give them permission to act on your behalf to delete data, then they go to work and your data goes away. All that's left is a progress log showing where they deleted it and how risky the site was. Incogni makes these data harvesters take your info down, and they keep doing it too, making sure that it stays down. Incogni is available risk-free for 30 days, so you can try it out and get a full refund if you aren't happy with the service. Use code IsaacArthur at the link in the episode description to get an exclusive 60% off an annual Incogni plan. Go to incogni.com/IsaacArthur and take your data back. So we're done for today, but we still have an episode this Sunday, June 30th, to look at free will, quantum mechanics, and theories exploring if the two might be linked. Then we'll head into July for a look at Roko's Basilisk, a strange acausal concept that might spell doom for humanity, and backwards in time at that. After that, we'll examine a different pathway for humanity with a look at cyborgs and cyborg civilizations. Then it will be time for our 2-hour feature-length summer special, the Interstellar Colonization Compendium, covering everything from the ships we'll use to get to other stars to how we'll use them and what we'll do when we get there. If you'd like to get alerts when those and other episodes come out, make sure to hit the like, subscribe, and notification buttons. You can also help support the show by becoming a member here on YouTube or Patreon, or check out other ways to help at isaacarthur.net. You can also catch all of SFA's episodes early and ad-free on our streaming service Nebula, along with hours of bonus content like in-situ resource utilization at go.nebula.tv/isaacarthur. As always, thanks for watching, and have a great week.